Now we are going to see the topic, the integrated rate equation. The integrated rate law for a first order reaction, zero order reaction, and half-life period, then pseudo order reaction. So everything we will see one by one. The first question, derive the expression for the rate constant of a first order reaction. The first order reaction is nothing but only one reactant gives the product. So already we have discussed in the last classes. Okay. So first order reaction, only one reactant gives a product. The next step, we should write the rate law for the first order reaction. So rate equal to rate constant with concentration A. Only 1 moles or coefficient we can say will come in the exponential power. Okay, the third step, what is rate? We should write the change in concentration with the time. The change in concentration of the reactant is decreasing, that's why minus dA by dt equal to rate constant concentration A. In the fourth step, the concentration will come in the left hand side, time will come in the right hand side. That's why the A will go here, then dt will come here. That is equation 1. Equation 1. Now the equation 1 we should integrate. The integrate about the equation between the limits of time t equal to 0 and the time equal to t, while the concentration varies from the initial concentration A0 to A at the later time. Okay. After applying the integral with the limit, we can write minus ln concentration A with the limit A0 A equal to rate constant K time the limit 0 and t. Next, minus ln A minus, so within bracket we should write minus ln A0. The limit will take place inside equal K T. The limits and all applied here. Okay. So next step, minus ln A minus plus ln A0 equal to KT. So how to write? Here plus ln A0 minus ln A. So simplify, ln A0 divided by A equal to KT. That is equation 2. Now ln equal to 2.303 log. In the place of ln, we can substitute 2.303 log A0 divided by A equal to KT. This equation is in natural logarithm, so that's why the ln is converted into usual logarithm with the base 10. That's why it is multiple with 2.303 log. So ln equal to 2.303 log. So finally we have to find only the rate constant k. So k equal to the time t will come in the denominator. Okay, so if you cross multiple means the previous step we can get it. There is a final expression that belongs to integrated rate law for a first order reaction, that is rate constant. So k equal to 2.303 by t log of A naught divided by A concentration. Now let us go to the second question. What are the examples of first order reaction? What are the examples of first order reaction? The first equation, dinitrogen pentoxide, decomposition of dinitrogen pentoxide, it gives nitrogen dioxide and oxygen. Only one reactant is present, so it belongs to first order. Likewise, decomposition of dionyl chloride SO2 Cl2, only one reactant. The product SO2, sulfur dioxide and chlorine gas. Then third equation is a good example for the first order, decomposition of hydrogen peroxide in aqueous solution. It gives water and oxygen, only one reactant. Finally, isomerization of cyclopropane converted into propene, both are isomer, only one reactant. So these are the examples belong to first order reaction. Next question, question number 3. What is pseudo order reaction? What is pseudo order reaction? Pseudo means false. Just you look the equation. The equation is nothing but ester hydrolysis. Here two reactants are present. But this equation considered as first order, pseudo first order. So why it is considered as pseudo first order? We will see. The two reactant, one is methyl acetate, that is ester, is added with water. It gives a product acetic acid and methanol, common name methyl alcohol. Okay. Now the reactant side we have to take the water. It is excess than the methyl acetate ester. The product of acetic acid and methyl alcohol belongs to the ester and not belong to water. Okay, simply we can write a second order reaction can be altered to a first order reaction by taking one of the reactant in large excess, one of the reactant which one water is large excess, that is called first order reaction, ester hydrolysis. Okay, by which how to write the rate law? So rate equal to rate constant, concentration of methyl acetate and water. The water is not considered because the product come only the reactant methyl acetate, not in water. Okay, if the reaction is carried out with a large excess of water, there is no significant change in the concentration of water during hydrolysis. From that we can find it, the changes occur only in the methyl acetate, not in water. That's why the concentration of water remains almost constant. Now we can understand why it is called pseudo first order. The product depends only on the methyl acetate, not in the water, because water is constant. Now how to write? Here from the rate law, rate constant K with water, we can write K dash. So finally the rate law, it is changing. Rate equal to K dash with the concentration methyl acetate, because water considered as constant. Next we move to the next question. Derive the expression for the rate constant of zero order reaction. Zero order reaction. Here I have given one equation, formation of hydrochloric acid. That is very simple equation. Hydrogen and chlorine in the presence of light, it gives 2 moles of hydrochloric acid. So if you want the hydrochloric acid, the product depends only on the light, does not depend on the hydrogen and chlorine, does not depend on the reactant hydrogen and chlorine, only depends on the light. So without light we are unable to get the product. So that's why it considered zero order reaction. So for the equation, the first step, rate we should write. Rate equal to rate constant K with the concentration A with the 0. 0 means zero order. Okay. So we know that anything power 0 assumed to be 1 minus dA by dt is for rate equal to K. So A power 0 1. The next step, the dt will go here. After that we have to take an integral. We should apply the limit A naught A, here 0 t. Okay. The next step we see. Here n is the order of reaction is not equal to 1. So that's why we have to follow this step. So 1 by concentration A power n minus 1 minus 1 by A naught concentration power n minus 1 equal to n minus 1 within bracket K into T. Okay, here the place of n, just you write 0 because order of reaction 0. So how to write 1 by A power minus 1 minus 1 by A power minus 1 equal to minus KT. Then we can get it, concentration A minus concentration A naught equal minus kT. Again we can write this equation multiple with minus, so minus A plus A naught equal to kT. Then we can write concentration A minus concentration A naught minus concentration A equal to kT. So K equal to concentration A naught minus concentration A divided by T. So the rate constant, concentration A naught minus concentration A by T, that is zero order reaction. Zero order reaction. Question number 5. Question number 5. What is half-life period? Half-life period. The correct definition we should write: the time required for the reactant concentration to reach one of its initial value. I give an example. You have to take the camphor, the initial amount 100 gram, just you assume initial weight of camphor 100 gram. Now the camphor is nothing but is made up of naphthalene. We know that the state solid turns to gaseous state. Gaseous state. Okay. When the time is going on, the 100 gram camphor turns to 50 gram camphor. So how much time it is taken? So we have to calculate. So make it half. 100 gram turns to 50 gram. How much time is taken? That time is called half-life period. I think you understood well. Let us move to the next question. Question number 6. Derive half-life period from the first order reaction. The first order reaction, just now we have seen in the first slide. The final expression first you write. The rate constant K equal to 2.303 by T log A naught divided by A concentration. Okay. Here A naught means initial, A final. Now you should apply the half-life period. The final concentration we can write A naught by 2. A naught by 2, and then T equal to T 1 by 2. The time will be half and final concentration will be half. Okay, after applying that, after applying in the first equation, so we can get like this. Now we should simplify this equation. The A naught will cancel, the 2 will come up, so we can write K equal to 2.303 by T 1 by 2 log 2. What is the value? Log 2, 0.3010. Just you substitute, and the 2.303 multiple with the 2.303 should multiple with the 0.3010 divided by T 1 by 2. So we can get 0.6932 divided by T 1 by 2. So finally we can get it. Half-life period T 1 by 2. The T 1 by 2 will come here. K will go down. So T 1 by 2 equal to 0.6932 divided by K. It is very simple derivation. Next question. derive half-life period from zero order reaction. The first order reaction just now we have seen half-life period. Now we are going to see the same half-life period from zero order reaction. Zero order reaction rate constant K equal to A naught minus A by T. Then final concentration A. How to write concentration A naught divided by 2 and T equal to T1 by 2. Just you substitute and we can get it. The 2 should multiple with the A naught minus A naught by 2 divided by T1 by 2. Then 2 A naught minus A naught means 1 A naught by 2 T1 by 2. Next, how to write the K? A naught divided by 2. The denominator we should write with the multiplication. So 1 by T1 by 2 we can write it. Finally, K equal to concentration A naught divided by 2 T off. The T off will come here because we are going to calculate the half-life period. So T naught will come here, K will go down. So T1 by 2 equal to concentration A naught by 2K. That's all.